the average disk. Okay, because as you can see through this graph, so some errors or this misclassification error was arised, and how you need to optimize this error. Okay, and there's a two classifications problem that we have seen, and there's a two different region that these samples are coming from the one class, but it is classified in some other class. So there is something called the error. Okay. Now, in this error, this whenever the error is coming up, then how you need to handle those type of errors. So your ultimate job, you need to design a classifier in such a way so that this probability of misclassification error will be less. So now today we are going to see that minimizing the average risk. So this whenever these some errors are incurred, then you need to attach some kind of penalty. Okay, so this penalty term will come, and this penalty can be captured in the form of the loss matrix. Now you need to first understand that this classification error probability, it is not always the best criterion, okay, to be adopted for minimization. So in general it is a thumb rule. So now and if you assign the same importance, this is because that if you assign the same importance to all the errors, okay, suppose this if you add the errors will have the different weights. Okay, the errors will have the different weights. If the errors will have the equal weights, then there is a no question of this kind of this loss things, okay, or these penalty terms. But if the errors will have the different weights, then you will have to think of it this cost matrix, or there is a cost needs to be incurred. How much cost that you need to optimize. If the errors are equal weights, so there is no problem. Only this probability, I mean error probability is enough for you. But if the error will have the different weights, okay, then the cost has to be incurred. Okay, so that is the main thing. So now the cost means that you need to minimize this average risk. If the cost is incurred, then you need to minimize this average risk. Suppose I'll take one example. Suppose in if you take one medical example, like it is much more serious for a doctor, okay, to make a wrong decision. Okay, suppose one patient visit a clinic and to diagnosis this malignant one tumor is that is this tumor is called the malignant tumor, and that if it is diagnosed as a benign one, I mean non-malignant one, then then there will be a problem in this case. But I mean, if it is actually a malignant, but it is treated as a non-malignant, so means there is a problem. Okay. Now, in this case, the other way that you can think, if a benign tumor, or you can say the non-malignant, is diagnosed as a malignant one, then the wrong decisions will be cleared out during subsequent clinical examinations. Suppose I'll just take one another example that in this way that the results from this wrong decision concerning a malignant tumor may be more fatal. So thus in these cases it is more appropriate that if you could assign a penalty term to a weight of each error. Okay, in our example that we have seen that if you could denote that W1 the class of malignant tumor, as you can see, and W2 with the class of the benign ones. And if you could see that let also R1 and R2, that if you could say as the regions of feature space where you could decide in favor of W1 and W2 respectively, then the error probability PE that can be given by, I mean, the following equations, that is that is you have already, okay, that here there is a no loss function, I mean loss is incurred. Now if you would like to, here you are assigning that here these errors are equal, I mean the error will have the equal weights, but if the loss is incurred, then you will have these two terms as you are using this two dimensional like this two class classification problem, then you will have this 2 cross 2 loss matrix. One will be L11, L12, then L21, L22. Okay. Now in the first one, then you need to minimize a modified version of this thing, that you will have this lambda 12 PW1, that here you will have just, yes, this is the things. Okay, here they minimize the average risk. So for each wrong decisions, suppose if it is not a malignant but it is treated as a malignant or the benign one, but if it is not a malignant but it is treated as a non-malignant, so it is an wrong decisions. For each wrong decisions, a penalty term is assigned. Since some decisions are more sensitive than others, then you will have you have to define a loss matrix. Okay, now this L will be defined as L11, L12, L21, and L22. So this is called a loss matrix. Okay, and it is only be applicable when the weights will be different. If the weights are same, so there is no concept of the loss matrix. In some books, if you see this without this, without if the weights are equal, and another is if weights are not equal. Okay. Now in this case, that we have L11. Can anyone switch off your microphone? Now you need to minimize this, that R is equal to that you have now have you understood the concept? This is called the error. So this is called the error one. So are you understanding this? What is alpha, lambda 1 or lambda 1 to lambda 21 and lambda 22? So now from the things that this confusion matrix will come up. Okay. So now let me design it on okay, so I'll just share it. Okay, so let me share my desktop, then only I'll just draw it. Can you see these things? Hello?
Yes, sir.
Okay. So now just let me draw it. Suppose okay. Now it is the decision rule. Here I should write decision rule. So it is the decision rule, and this one is actual. Means actual class. Okay, and it is class 1. I mean X is class 1. It is class 2. It's class 3. Suppose, and also here class 1. Class 2, class 3. So this is actual. Okay, now you apply some decisions rule. Suppose x is a point that needs to be classified. Okay, so now if x is actually from class 1, suppose I am taking one x some point, suppose x I am taking one point. Now x is actually from class 1 and is after applying some decision rule. I mean, suppose you are applying some base decisions rule, it is classified in class 1, then it is absolutely fine. Suppose if I am making it as a kind of thing, some tick. Okay, ticked one. Okay, x is actually from class 1 and it is classified in class 1, then it is absolutely fine. So there is no error is occurred. Now x is actually from class 1 but is classified in class 2, then there is an error. Okay, there is an error. Now x is actually from class 1 and it's classified in class 3, there is an error. Similarly, x is actually from class 2 and after applying the base decision rule, it is in class 1, then there is an error. Now x is actually from class 2 and it is classified in class 2, then it's fine absolutely. So now it is absolutely fine. Now if it is actually from class 2 but it's classified in class 3, now there is an error. Similarly, for it is these things, and if it is okay. So are you understanding me? That this loss matrix that I have been drawn over there, that is an L11. As you can see, L11, L12, I mean L11, L22, L33, all diagonal elements are correctly classified. And the rest of the things like L12, L13 or L21, L23 or L31, L32 are not, these cells are not correctly classified. So now there is a penalty terms that you need to introduce. So this matrix is called this confusion matrix. In the last class we are talking about the term is called the confusion matrix. So from what is this meaning of this confusion matrix? Okay, so now this is the thing. So it is an error. Now here we are going to have this error. Now this is an error is occur. Now each error will have equal-weights. If the errors will have the equal-weights, so it's fine. So only you need to consider this probability. The cost of misclassification and the probability of misclassification both are different. So please understand, the cost of misclassification and the probability of misclassification both are different. If you are assuming this is a cost of misclassification, then you need to add this penalty term. This probability of misclassification means we are assuming that you are not incurring any cost. We are assuming that the probabilities, I mean cost, the weights of each error term is equal. Okay, so this is very important things. From this concept, you could design a confusion matrix for any classifier that you are going to use, any classifier. Then you may encounter this type of problems. One is called that you need to develop a confusion matrix. In the confusion matrix, you will have the decision rule, and the decisions rules mean that it will just tell you that efficiency of the classifier. If your classifier are smart enough, then the points that you're going to classify, if it is actually from class 1 but it is classified in some other class, then there is a problem. And if this actual is from one class and your classifier also classified in the correct class, then there is no error. Okay, So now here this loss matrix that you are seeing here, this is the concept. So now as we can see that the points, if you take this point, that for each term, so if you not use I mean any factors like these errors are equal, so there is a no concept of the loss things. There is a cost will not be come into this picture, but here you need to consider these important things is that cost will come into this picture here. So that's why you need to design a loss matrix. So means wherever you are going to classify it, so you need to consider this loss matrix. Actually, it is for the mathematical definitions. Okay, you need to understand this mathematical definition, and so these things has been drawn from the graph. So the graph that we have been drawn over there. So in order to understand these each and every term, one is the diagonal elements, another is the non-diagonal elements. So now this confusion matrix needs to be clear to you. Okay. So now here this lambda 1 2 is the penalty term for deciding the class W2. Okay, and although this the pattern belongs to W1, because the patterns is belongs to W1, actually patterns is belongs to W1, but it is classified in W2. So that's why this error term is this lambda 1 2. Okay, are you understanding now? What is the meaning of the lambda 1 2? The pattern is actually from class 1, but it is classified in class 2. So that's why this penalty that is occurred and the penalty is caused, and you need to minimize these things. So that's why this lambda 1 2. Similarly, for the lambda 2 1, this pattern is actually from class 2, but it is classified in class 1. Okay.
Sir, excuse
Yes.
me, sir.
Huh.
Sir, we are applying here penalty. That means base decision rule is part of model training.
Yes, because the data points that you are going to have, I mean, you want to test it. Whatever test sample that you are going to have after classifying this pattern. Okay, pattern means this set of observations. Okay. After applying the base decisions rule, that whenever you are going to add it, classify it using the base decisions rule, so you are incurring some penalty, because the pattern, you know that this pattern belongs to the class 1. You know that this test pattern that I am going to classify it is belongs to class 1. I mean, it should be belongs to class 1, but after applying the base decisions rule or any decisions rule that you are going to have, then it is classified in class 2. It means there is a penalty. Okay, so now whenever you are going to have some penalty, then you are going to have some risk. So now this term, this is a lambda 1 1. I mean lambda 1 2, lambda 2 1, lambda 2 2. So I mean all this is a penalty term, and this penalty term is being constituted for the loss matrix L, capital L. So capital L is called the loss matrix. Where in the loss matrix that I have in the paint I have already been drawn. So now this matrix, okay, and from where that it is coming, and you need to find this. What is the risk? So risk is called the R1 for this class 1. If the pattern is actually from the class 2, but it is classified in class 1, then the risk is occurred R1. Then also you need to optimize it. And this pattern actually from the class 2, but it is classified in class 1, then also you need to consider the risk, because this R1 and R2 both are coming from the lambda 1 2 and lambda 2 1. Okay, because here these two penalties are coming, so that's why you need to have the two risks, R1 and R2. Now, so that is why this term risk with respect to W1, that you need to consider that R1 is equal to lambda 1 1 into Px W1 into dx. Okay, and then R1 is equal to this is Px W1 dx plus this term that you need to actually this rectangular term, that box that is there, lambda 1 to R2 Pxw1 into dx. It means that it is actually from class 1, but it is classified in class 2. So that's why these things has to be optimized. These things is clear. I mean, this is it is actually classified lambda 1 Px1 because it is actually from class 1, but also classified in class 1. So it's fine. So there is no penalties occurs. But here the concept is that these things has to be optimized. So that is why it is being there. Next is risk with respect to W2. You just say these things, opposite things, R2. Then this rectangular box 1, you need to optimize it. Okay, lambda 21, it means whenever you are saying lambda 21, it means that pattern is actually from class 2, but it is classified in class 1. So now whenever it is classified in class 1, you need to estimate the error. So error means probability of the misclassification error. So that's why P of xw2 dx, because it is a density function and area under the curve is 1. So that's why that we have using this term that we have already discussed in the previous class. So now you have two terms, two risks, R1 and R2. So because if it is a multi-class classification problem, you have R1, R2 till Rm. That many terms will be there. Here we are only concentrating this 2+ classification. That's why you have the R1 and R2, two risks. Okay. Now next is that these probabilities that is in the rectangular box. This is the probabilities of wrong decision. What is the wrong decision? That if you take the example of this tumor is malignant or it is a benign. Okay, it is actually a malignant, but it is showing it is a non-malignant. Which one is harm? But it is actually non-malignant, but it is showing that it is malignant. So in your portion, which one is be acceptable? Because you need to assign some weights of the error. You need to assign some weights of the error. Suppose I am taking one example to understand this thing. Suppose if I am saying the fees of your semester is going to be waived off for this semester. This is one statement, and this one statement is being uttered by two different people. Suppose the fees of your semester is going to be waived off for this semester. Now, if it is if the statement is made by me and it is attributed to our director sir, then its consequences will be enormous. But if the statement is made by our director sir and if it is attributed to me, then it's fine. I mean, I had some mistakes, or if one of your friends has been attributed to this thing, it's fine. So you have some mistakes, then it can be negotiable. Okay. So now its consequences won't be so much. Are you understanding? Or if you take any type of example in these things, then if I say that tomorrow we are going to get our COVID vaccines. Tomorrow we are going to get our COVID vaccines. So if this statement is made by me, but it is attributed to our Honorable Prime Minister, then its consequences will be enormous. But if this statement is made by our Honorable Prime Minister, but it is attributed to me, then it's fine. So or any one person, if it is a media person, then he may be sacked or kind of thing. So it isn't like that. So it depends that how you are going to put in the weights on the errors. Are you understanding me? What is the actual meaning of the penalty terms? And it is based on this, how much these weights that you are going to provide for this corresponding error. So now these are the terms that probabilities of the wrong decisions, that if the person is actually having a malignant tumor, but the doctor is diagnosed as a non-malignant, then there is a problem. Then there will be a problem. But if the person does not have the non-malignant, actually not having this malignant tumor, but doctor is saying this malignant, it's fine. So you can also have other treatment. I mean, you can also see other things. Okay, so some false alarm that is being coming up. Okay, so now these are the things that in pattern recognition or in the machine learning, whenever you are going to have apply some classification techniques, you are going to have some false alarm. You are going to have some false alarm. Now you need to identify that a false alarm. Now the average risk.
Sir?
Yes.
Hello, sir.
Yes.
Sir, you talked about confusion matrix. Sir, confusion matrix contains the probability of a point being classified to a particular class. Is it that?
Yes, you can tell in this way also, because actually it is not this probability actually. So it is that the points, that is you know that this pattern is belongs to this particular class. Okay, suppose you have total I mean 10 classes. So the size of the confusion matrix will be 10 cross 10. Okay, and you are going to have your test pattern is total. Actually, you will have some numbers. So in the confusion matrix, you will have some numbers. Okay, out of this pattern, out of the 100 patterns, or if you take this 40% of the entire data set as a test data set, and if the 40% is a total 200 data points, or the 200 points, now out of the 200 points, how many points are belongs to the which class? And these points that is going to have, so before classifying it into table, okay, you need to compute its this probability of the misclassification in background. Okay, in background, I mean, after applying the Bayes decisions rule, so you will get only two answer, binary answer, yes or no, 1 and 0, isn't it? So there is a formula, capital
Yes, sir.
capital Pi small pi is greater than is equal to capital Pj small pj. For all I is greater than j, isn't it? You have a density function that is multivariate Gaussian. You have the prior probability which is given to you, and if any test pattern comes to you, you checked it, you will have the answer 1 and 0. If it is 1, then you can put it ith class. If it is 0, in this 0th class. So now, if it how many test pattern that you are going to have, you just fill it up in the confusion matrix. So here in this probability, capital Pi, it is a probability value. Density function, it is a probability values. You'll have to just multiply it. So that is this. I mean, the decision is going to be taken up. So it is based on the probabilities values. But in if whenever you are going to fill it up, so you will just have the numbers. Okay.
Okay, sir.
Is that clear? Now, next thing is average risk. So this risk you need to optimize. Now, are you understanding that that is the meaning of the risk? Okay, so this is the risk R. Okay, so now the average, we are trying to do the minimizing the average risk. So that is your job. R is equal to R1. R1 means that we have already seen, this is a R12, PW1, capital PW1, okay, plus R2, that is PW2. Here this is an PW1 and PW2 that is being there. It is an we have already seen it is in prior probabilities, and you have to also sing. And if the R1 is missing, then it means that this we are assigning that the errors are equivalents. If you simply have the capital P1 integration of R1 small p x W2 dx, and this capital P2 integration of R2 px W2 dx, it means that you are assuming that your weights are equivalents. Your weights are equivalents. Okay. Now these things, this how to do this thing, how to minimize this average risk, that is to be considered, and you need to do it. How do you do it? Now you have to choose R1 and R2 in such a way so that R is going to be minimized. That is your job. You have to choose R1 and R2 in such a way so that this R is minimized. Then you have to be, you have to assign that minimizing the average risk becomes equivalence. I mean, it is, so what exactly you can quantify the term minimizing the average risk? It is equivalent to minimizing the classification error probability, because this R1 and R2 that we are having, it is the region where the misclassification error is occurred. Okay, and you have already identified with this density function. So now this minimizing the average risk becomes equivalent to minimizing the classification error probability. Now, if you have the two class, if you are going to have the two class case, now for this specific case, you could obtain that this x will be x. You can assign x to wi if this condition is satisfied. That is an L1. L1 is equal to L11 PXW1 PW1 plus L21 PXW2 PW2. You have already seen it is less than that L2, that is L12 PXW1 PW2 plus L22 PXW2 PW2. Now you assign W1. Now you are just going to have apply the base decisions rule. Okay, capital Pi small pi is less than equal to capital Pj small pj, but here we are just ignoring the equivalent term. We are going to consider only this less than. Now you can assign x. You can assign x to W1. Okay, so just a minute. Hello. Hello. চলো আমার একটা ক্লাস নিচ্ছে, একটু পরে ফোন করছে, ক্লাস চলছে। Okay, now in the for two class, for this case, yeah, you could assign x to W1. Okay, if L1 is less than L2, that is, if you just do the arrangement of the terms, what you are going to get? So you will have simply you will have lambda 21 minus lambda 22. Actually, here this step jump is there. Okay, I'm just explaining to you. You just do this the arrangement. Okay, you assign x to wi if L1 is less than L2, which is nothing but lambda 21 minus lambda 22. It will be within bracket PXW2 capital PW2 less than lambda 12 minus lambda 11 within bracket PXW1 capital PW1. You can simply do it. You are just bringing all the terms of these things in the left hand side, and you are going to just bringing back all the terms to the right hand side in such a way so these things can be formulated. Now it is so natural. It is so natural to assume that this lambda ij, they say 1 2 lambda ij obviously greater than lambda ii. Okay, it is so natural to assume that lambda ij means 1 2 term where the error is occurred. It is greater than lambda ii because the correct decisions are penalized, which is much less than the wrong ones. Okay, it means that you can have the correct decisions are penalized, which much less than wrong ones. Now, if you could adopt these assumptions, now this decisions rule for a two class classification case can become that you can assign x in W1 or you can assign x to W2. Okay, if L12, okay, so this is called a likelihood ratio. If you have, that is the likelihood ratio L12 is equal to PXW1 divided by PXW2, which is just a density function. We are just going to, so we have already seen that PXW1, it is a, what is it? It is a likelihood function of x with respect to x, that we have already seen. So now L12, which is equivalent to PXW1 by PXW2, which is greater than or less than, that is PW2 by PW1 into this loss term. Okay, what is it? Lambda 21 minus lambda 22 divided by lambda 12 minus lambda 11. So this L12 is called the likelihood ratio, and the preceding test as the likelihood ratio test. Okay, and this loss matrix, so you could assume that this loss matrix in the form of, if you simply have L is equal to 0. Yes, if you consider it, if you consider the your loss matrix capital L is equal to lambda 1 1 0 and lambda 2 2 0. If you simply have, because there is a, it is correctly classified, and if it is 0 0, then it is 0 lambda 1 2 and lambda 2 1 0. Then if misclassification of patterns that come from the W2, if you simply have which is considered to have the very serious consequences, then you could choose lambda 2 1 is greater than lambda 1 2. Okay, now this pattern is are assigned to class W2. If this condition is satisfied, PXW2 greater than PXW2 greater than PXW1 into lambda 1 2 divided by lambda 2 1. That is being written over there. And if it is W1, then if PXW1 is greater than PXW2 in this case. So this is these things. This is a special case. Because in every case there will be a special case. What is the special case? If the prior probabilities for both the classes are equal. I mean, if it is equiprobable class, then PW1 is equal to PW2 is equal to half, and in this, in your penalty term, is lambda 1 1 is equal to lambda 2 1 is equal to 0. Then if it is 0, your loss matrix will be 0 lambda 1 2 and lambda 2 1 0. Okay, and these things is to be multiplied. And if lambda 2 1 is equal to lambda 1 2, then it is a minimum classification error probability. And if you have PW1 and PW2 is equal to half, you can assume it, and that is PXW1 is multiplied a factor which is less than 1, and that you could have that if you see the region, that is this R2 will be increased while this R1 is decreased, and also it will be true for this other case also. Okay, so this is this whole things that I was talking about. So if you find this some loss, then this loss can be treated as in this way. Okay, so one is special case that you have that is 0, then you have this term. You just simply have, you just simply put it this value if X is classified in W1 or it is classified in W2, and you just simply apply the base decisions rule. Capital Pi, small pi is greater than the capital Pj, small pj, where I is not equal to 0. So that is this formula for the base decision rule. Then you could get this answer. Okay. Here some example is there. Here some example is there. Suppose in a 2-class problem with a single feature vector x, the probability density function are Gaussian with variance sigma squared is equal to half for both the classes, and the mean values, okay, are 0 and 1 respectively. That is Pxw1 is equal to 1 by root over 2 pi exp minus x square, and the density function for Pxw2 is equal to 1 by root over of pi exp minus x minus 1 whole square, where Pw1 Pw2 is equal to half and L is equal to loss matrix is equal to 0, 0 0.5, 1.0 and 0. Now what you have to do, you have to compute if Pw1 is equal to Pw2 half, then you have to compute the threshold value x0. You have to compute the threshold value x0 in such a way for computing this minimum error probability and for minimizing the risk if the loss matrix is given. So can you do it? So 2 density function is given. Okay. Now the question is that you have a 2-class classifications problem with a feature vector single feature x, and the PDFs are Gaussian with the variance sigma square is equal to half for both the classes, and mean values are 0 and 1 respectively. For one class it is 0 and another class it is 1, and the density function is given to you, and if Pw1 is equal to Pw2 is equal to half, Then you have to compute the threshold value x naught for minimum error probability and for minimum risk. If it is for the minimum risk, then the loss matrix is given L 0, 0.5 and 1.00. What will be your answers? Can anyone just give me the idea? That's it.
Sir, as lambda 1 2 is 0.5, it will move towards the left of the
Towards the
left.
Towards the left. Okay, yes. And the thresholds move towards the left. Very good. Okay, and what will be the value? Left of. So you need to consider some value. X naught will be some value.
Yes, sir. Yes.
What will be the threshold? What will be the threshold? X naught will be some. You can simply what you have to do. So you're correct to some extent. Firstly, taking into account what you have to do, that the threshold for this minimum error, this probability x naught will be, then this threshold will be half. Okay, and these are the things. This is very simple things. You can just take the logarithm in the both side. I mean, you have this exp of minus x square and exp of minus x minus whole square. You take the logarithm in the both sides, and you have end up with the x naught is equal to half. Then you the minimum risk case that you would get x naught is equal to x of minus x square minus 2x of x minus 1 and whole square. Okay, and which will have this x naught 1 minus ln means log. If you take the log by 2, which is a less than of half. So this is the threshold which is moved to the left of the half. And if the two classes are not equiprobable, then it is easily verified that if PW1 is greater than or less than of PW2, then the threshold is moved to the right. If it is equiprobable, then the threshold moves to the left of half, and if it is not equiprobable, then this threshold is moved to the either left or right based on the conditions. PW1, I mean prior probability, PW1 is greater than or less than the PW2. Okay, I mean if you just expand this region in which that we decide that which are the most probable classes, and this is this case that you could have. Okay, and this is the pictorial representation that you would get, that is PXW1, that is an x naught, and if you just equiprobable class, then you will have this moves to the left. Okay, if it is not equiprobable class, based on these conditions, that you have either in the left or in the right based on this prior probability. Now one question comes to you. I just wanted to ask you. So there is a concept that you have a data points. You have finitely many points. You have finitely many points given to you, and for the finitely many points that you have the firstly you have set of observation, and in this set of observation you have finitely many data points. Now how do you ensure it that which distributions that your data needs to fit it? How do you ensure it that which distribution that you are going to need to be fitted? Now if you are somehow managed to fit the distributions, next question comes, how do you estimate the mean and covariance matrix? If somehow you are managed to fit the distributions, now then how do you estimate the mean and the variance or covariance? Now in statistics, as I already told you, in statistics, in the statisticians, what they are going to do. So firstly, they are going to fit. There is a concept is called the fitting a distribution. So in some of you asked me one question in the last class, sir, how do I check that which distribution is important for my data sets? Which distribution is important for my data sets? Okay. Now I will tell you only a way of doing these things, and my answers will be this is not a actual, as it should be a approximate answers. It's a partial answer that you I would rather say. The question is that if suppose if you do not know the what is the distribution of your data, you do not know this actual distribution of your data. If you know this actual distribution of the data, you can easily estimate this mean and variance or mean and covariance. But if you do not know the actual distribution of the data, then what do you have to do? So first of all, you need to know there are several distributions are available. You have this binomial distribution, you have Poisson distribution, you have normal distribution, you have beta distributions, you have uh, F distributions, you have chi-square distribution, you have Cauchy distributions, you have the plenty of distributions. So now the statisticians would like to do, firstly they just fit a distributions, any arbitrary distributions, you just fit a distribution and they find the value. What is the value? They find the chi-square value. They find the chi-square value, and if the chi-square value or simply the observed chi-square value, if it is less than the tabulated chi-square value, then it is said that you have fit, you have this distribution has fitted for this particular data set. So this is the A way of doing these things. That's it's called the chi-square fitting, and the fit, the test that you're going to have, you're going to have some test that your observed value, observed chi-square value, if it is less than the tabulated chi-square value, because this tabulated means so there is a for each distribution, so there is a some table is given, will be given. You have the F table, you have the chi-square table, you have the T table. Okay, now the test that you're going to have, so this is called the chi-square test. So the test is commonly known as a chi-square test. Okay, and this test is not this actual test, because as you are going to estimate this distribution, you are going to estimate this you are going to try to fit the distributions, fitting the distribution for a finally many data points that you are going to have. So that's why if the distribution is not known to you, then it is called the approximate. The test is called the approximate test. The test is called the approximate test because you are approximating the distributions. And if you know the distribution correctly, then this test is called the actual test. So there is a two type of test. One is called the actual test, another is called the approximate test. As you are trying to approximate the distribution to some chi-square distribution, okay, you are fitting a distribution. Suppose you are going to apply this. This is an any distribution, any arbitrary distribution. I am trying to find this chi-square value. If the observed chi-square value is less than the tabulated chi-square value, then you are saying this somehow you manage to fit the distribution. Okay, so this is the way. So now next is called the discriminant functions. So that is more important things that people are using. That is a discriminant function for the decision surfaces, and it is very much useful in the different cases that we need to see. And actually, this function, that is if R1, Ri and Rj, you have these two regions. I think you have understood the concept of the region are contiguous. Then you have these two. You have a function, discriminant function, that is a gx, which is a pw1x, or you can have this decision surface in a multidimensional feature space. And this for the minimum error probability, it can be described by the equation that is gx pwyx minus pwjx is equal to 0. From the one side of the surface, the difference is positive, and from the other side of the surface, the difference is negative. Okay, and sometimes it may happen that instead of directly working with the probability or the risk functions, it is more convenient that if you understand the concept in a mathematical point of view, and if you just develop to work with an equivalent function of them. For example, that if you have the gx, gxi equivalent to you have that gxi equivalent to, that is a f of pwix, where f dot is a monotonically increasing function, or it is a monotonically non-decreasing function. You know the meaning of the monotonically non-decreasing function? Anyone?
Sir, the function is state.
Yes, sir.
First order derivative.
Okay, good, very good. So now this function, it is called this monotonic function, and the rules remains the same. If you use that this gx is equal to that it is f of pwix, where f dot, so where f dot means that is it is a monotonically increasing function, and the gix is known as a discriminant functions, and you can use it as, you can classify x in wi if gix, if you have gix greater than gjx for all j is not is equal to I, and the decision surface that you are going to have for separating the two regions R1 and R2, that can be described by gix will be gix minus gjx is equal to 0. So that is the concept of this thing. Okay, so that is the main concept, and obviously we will have a lot of discussion on the decision surface on the discriminant functions. So in general, this discriminant function, that is gix is equal to f p wix. Now if you have this decision surface, whenever we are talking about the decision surface, it means that it's separating the contiguous regions. So contiguous regions between these two spaces. Okay, as you can see, if you have one line, so line above the line it is one class, below the line it is another class. So now these functions can be defined as independent of the Bayesian based decisions rule. It should be, this is an independent of the based decisions rule, and it is a, you can get these suboptimal solutions. Okay, and also that if you chosen appropriately, it can be computationally more means tractable. So that is the concept. So we'll have these things. And next, that we have already seen these multivariate Gaussian distributions. So now we need to establish some classifier from the Bayes decisions rule. You can establish a formula of this minimum distance classifier, because you had one assignment of the minimum distance classifier. So now from where it is coming? So from the Bayes decisions rule, with some assumptions that you could develop or you could derive a minimum distance classification rule, or this is called minimum distance classifier. That we'll see. So I'm just today introducing it, that I'll just, tomorrow I'll be explaining to you how you can establish with some assumption that you could get this like this minimum distance classification rule from the Bayes rule. So now this multivariate Gaussian PDF formula is that fx, or you can have the px w is equal to 1 by root over 2 pi to the power m. Here m is not this writing, here it is writing this L. L is L dimension. But in the last class, you have seen that we have written this capital M, I mean M dimensions, but here it is written L. So don't be confused with this thing. Okay, into, I mean, sigma, determinant of sigma to the power half. Okay, determinant of sigma to the power half, exp of minus half x minus mu. So we are writing this is an, actually we are writing this mu. Okay, so for the different class, ith class, jth, for each class. Okay, so that's why it is written this I. So x minus mu y transpose, x is a vector. Okay, mu is also a vector. Then sigma inverse x minus mu, where mu is equal to, that is this is an E of x, this matrix, and as it is a L cross L matrix in Wi, because as it is considered in the form of the W, but actually it is a mu is a column vector. It is an I mean n cross 1. Okay, and this is a covariance matrix. So this, so now there we are going to estimate. So here what you are going to do, here you are going to estimate. So if the distribution is known to you, then you need to estimate its point. So mean is a point. You need to estimate this. One thing is that in statistics it comes, you need to fitting a distributions. After fitting a distribution, you need to estimate its parameter. Estimating this parameter. Okay, so there's a two things: estimating the parameter and estimating the density functions. Okay, so now if you are assuming that if your distribution is known, then you need to estimate this parameter. So there is a different concept is there, that's called the maximum likelihood estimation. So we'll see one of the very important concept is called the maximum likelihood estimation. So anyway, so we'll see all these things. So I'll derive it how from these things concepts you could you could get that these things there is a certain condition is there from these things. So if density, if the multivariate Gaussian is given to you, and so we'll have the different cases, case 1, and this is in case 2, and you have the case 3. Now case 1 will be the if the all the prior probabilities are equal. If the all prior probabilities are equal, that is 1 by C, P1 is equal to P2 is equal to Pc is equal to 1 by C, and your variance covariance matrix are also equal, and also an identity matrix, and the distribution is a normal distribution. So under these certain assumptions, so we could establish that from the base decision rule you can derive the minimum distance classifier. First assumption is that all the prior probabilities are equal. Second is that the distributions is a normal distributions. Third one, that all the variance covariance matrices are equal. Not only equal, that it is an identity matrix. Then under these assumptions, you could derive this minimum distance classifier. Okay, today I'm stopping it. So tomorrow, so I'll be deriving, I'll be showing these two different cases. Okay. So any questions you can ask me. Yes.
Sir, will you upload this slide?
Yes, I'll upload these slides because I have my own notes. So I'll just I'm just preparing my entire notes. Okay, and actually these slides that I'm following from the book of, this is a theoretics book. So I can share these slides to all of you. There is no problem. Okay, but you can prefer the book is, I mean, this is theoretics book and the Dudard book. So I mean, more or less the contents are same. Okay, but I am having my own notes. So I'm preparing these notes tomorrow. In the tomorrow class, I'll be demonstrating with my own notes so that it will be more easy. Because sometimes in the Duda book and other things, so you will get involved in a lot of mathematics. Okay, but obviously it is a good mathematics. If you if I just simplify the mathematics in a more simpler way, it will be more clear to go through it. Okay. So that's all for today.
Sir, could you please send us the PDF of the books?
What? I didn't follow you.
Sir, PDF of those books.
PDF of
From
okay. PDF. I have the PDF of theoretics books, and these slides that I am showing and from the theoretics books. I mean I can send you today, and also this, but I don't have currently this PDF of this Duda book. Huh? So you please search it. Okay, so I'm just disconnecting. Yeah.